Uh, right, Long, I did notice that your exam was missing. I guess you're here somewhere. That your exam was missing. I don't know exactly what to do with that. I have to make a decision. I know you tried to upload it, but you turned it in late. Of course, I won't totally discount it, that's for sure. But I don't know exactly what I'm going to do. I may have to, take a few points off or something because you did turn it in late. I know you realized it late. I also realized it late.
Well, I turn it in time, I think, but it's just
okay,
like
I'll check at the end. I just didn't have time to process that situation. Because I have to make a decision. If you turned it in immediately at the end of the exam, then I would just. But if it was significantly later than the deadline, then I may have to take some points off for being late. I don't know. But no, I know I saw that your file was empty on the Canvas. I have. So are you saying that when you sent it through email, what time was that?
That was 2:40, 2:38 actually. 2:38.
2:38. So you sent it early?
Right. And then so
Uh-huh.
when I put it in the document and uploaded the canvas, that was before 2:50. And then for some reason on the canvas it just my pictures weren't there when I checked it last night. But you can I shared the link with the Google Docs with all the photos of my work, and the last edit was at 2:42
Long.
p.m.
What do you mean? Like, okay, that's a situation. I'll check it. What the email that I got, I'll check what
Okay.
time you sent that. If it was sent
Okay.
reasonably within the time frame, that would be fine.
Oh, the email I sent it last night because I just realized that the photos weren't
It wasn't
on
right.
canvas, weren't showing up.
Right. So that's the point, that by the time I received it, it was already past time, past due. Now I understand that you made it, that you just didn't upload, or they didn't show, or whatever. I'm not gonna. I'll have to see. I don't know. At this point, my policy was that if you submit it late, I have to take some points off. In your situation, I'll have to consider what the situation is. Send me that link you say that is in your Google Docs or whatever.
I did. It's I sent you through email.
Okay, I'll check. I don't know if that's is there? You're saying in that Google Doc there's a place where I can verify the last time that it was edited or something like that, right?
Yes.
Okay, I'll try to do that if I can verify that. Don't touch it. Don't edit it.
Yeah, I haven't touched it yet. So
if I can verify that's the last time that it was edited at a particular time, then I could download that version, whatever version that happens to be, and grade that. If that's what you want me to do, I could do that. If it says that clearly the last time it was edited, it was at this time.
right, and also I have the photos taken at a specific time on my phone. And if you want me to send that to you as well,
Well, I cannot grade a little bit here, a little bit there.
okay.
What I can do is I can go to Google Docs, and if it really says edited at this time, then
Right.
I'll sure I can grade that if it's by that time.
Okay.
That's not a problem, right?
Okay.
So
Thank you.
Right. So give me a chance though to over break. We'll definitely clear it up. And if I cannot verify, if I can verify it, that's fine. If I cannot verify it, I wouldn't deduct that much anyway. But if I can verify it, then I won't deduct anything. Okay.
Okay. Thank you.
But it has to be verified for the whole exam, not for a piece of it or something. But
Right.
you're saying the entire exam is in that Google Doc. And
right.
When it was okay, that sounds reasonable. Yeah. Okay.
Thank you.
I obviously haven't done any of that though, so I'll have to get to it. Okay. Right. So my plan for today, I had one plan. Let's see. I think what we should do, there's 26 of us. I'm going to go over the exam. I think the best option is I did want to have one thing to teach today, which is this issue of resonance for RLC circuits, which is something that you do see in the lab. And probably they're still trying to explain that to you. I wanted to explain that to you myself. So I was hoping to get to that today. Now, perhaps the best, my plan is to do nothing on Wednesday, have no new material at all. So basically Wednesday, what I would like to use the entire day for is to go over grades, whoever wants to do grades. As you can tell, I just kind of finished most of the grades, but I still haven't really figured out exactly how I'm going to grade things. The problem that I have this case is usually when you say you're going to make it something easy, it turns out that it's not that easy, but actually there were multiple perfect scores for this exam. There is class on Wednesday, right? There's not on Thursday. Is that true that there's class on Wednesday? I was just going to do grades. Well, somebody, oh, it's a non-instructional day. Oh, okay. I see. Okay, that's fine. I didn't realize, I thought it was just Thursday and Friday, but Wednesday as well. Huh? Oh, they changed, that's right. They changed the policy on that stuff at some point in the past. Well, we can do grades when we come back if you want. I'd certainly, yeah, let's do that. When we come back, we can, or we can start today, but I did want to go over one thing, just one thing today. That was my plan. No class Wednesday, Thursday, and Friday. Oh, okay. Okay. Well, that makes my life easier in some sense, more break for all of us. We can start with grades, but the problem I have with that is I've been grading a bunch of classes and I don't know exactly how I'm going to grade it yet. That's what I was getting into right now. So it probably makes more sense to discuss individual grades after the break. I was hoping to do it on Wednesday, but after the break is fine. So we can use after the break, we can take time to do grades. I graded the exams. I did have a bunch of perfect scores in the exam. So that's good, that's nice. Of course, you know, on your end, you like it when you do perfect, but the problem is that makes it a little hard to grade because people are pre bunched up at the top. So again, I don't usually get exams where I get perfect, multiple perfect scores. That's, you know, I usually get 1, 2, or 3, maybe maximum 3. In this case, I got at least 5 or 6, I think. So quite a few students did, if not perfect, next to perfect, you know. So that makes it a little harder to, so what ends up happening in situations like that is that it puts a little bit more pressure on the final to come up with a better grading system, because again, if everybody's bunched at the top, it's a little bit harder to say, okay, this person deserves an A, but not this person. This student deserves a B. So it's a little harder when so for once I managed to do the exam, you know, usually I think I'm going to make it easy and it doesn't happen. It doesn't turn out to be that way. There's something that still makes it, but this time it seemed like I did make it easy because again, the mean was very high and there were multiple students that got perfect scores. Right. So I'll tell you how I'm going to handle that. Usually the curve, when the exam is low, the curve puts people up. You know, I guess I could just not curve this one. That would, I'm sure some people would like that. Let me think about that. I just actually don't have the answer to that. But anyway, if you have some, I'll have the answer for you for sure after break, how I'm going to handle it, what is the mean, what I'm going to do with this exam. Am I going to curve it, not curve it, and so on. I'll have to think about it, play around with the grades a little bit to see what happens, what the grades come out to. But anyway, if somebody really wants to discuss their particular situation today, can't wait until after break for some reason, then let's do that. Hopefully not that many of you, so we can I can teach a little bit today. But right after break, we can take care of the, so perhaps the class after the break, we can just devote that one for grades. If there is enough of you who want to go over grades, we're doing okay with time, so I don't think there should be a problem taking time out to discuss grades. But anyway, yeah, okay. So no class on Wednesday. So no, Canvas doesn't do anything, Trent. So I know students sometimes they look at Canvas, they get worried. It doesn't mean anything. Canvas doesn't. So it doesn't do any curve, anything. It just gives you the grade. That's the point total. I did mention the last time how that I did curve the first exam. But again, let me just collect. I just got done grading, and I have a bunch of other sections to grade. No, why would it be? The only thing that Canvas says is the total, the point total, and how many points you got. That's it. There is no grade. There is no curving in there. So I mean, I'm not saying the information is worthless. You have the point total for the exam, which corresponds to the sections, each section, the multiple choice part and the other sections. And then you have And then you have that's it. And then you take a ratio if you want, but that's not a curve. That's just a percentage. Are we going to have another homework assignment before the end of the year? Yes, before the end of the year, for sure, you'll have one more, yeah. This is I'll do the RLC circuits, possibly a short one and a little bit longer one. Yeah, that's right. The percentage, you can get the percentage from Canvas, but not the curve. I'm not sure. Is that somehow confusing? I'm not sure what is confusing about that. Percent just means you take you divide the total, your number of points. That's not a curve. There is no curve in that. Okay. Now, what I was saying, of course, we did discuss the curve for the first exam. I forget what it was, but we did discuss the curve for the first exam. What I'm saying is that I'm not sure what I'm going to do for the curve in this exam, because the curve will not help anybody. If anything, the curve could bring people down. So I'm sure you prefer me not to have a curve for the second exam, since the mean of the class was pretty high. So that's what I was saying about this exam. So I haven't decided how to handle it yet. Any other questions about that? I mean, to me, it's pretty straightforward what I'm saying, but I'm not sure. It sounds like it's getting people confused. I'm not really sure why. I didn't curve it yet because I don't know if I'm going to curve this exam because the grades were so high. That's what I'm saying about that. Okay. Okay, so let's go through it anyway. And then again, if somebody still they're worried about something and they really want to take care of it right now, then let's discuss it after class if you want. But I won't have the curve. I don't even know if I'm going to use a curve, so I won't be able to give you all the details that you might want to have. Now, as usual, you should also be checking your Master in Physics score to figure out your grade. But I can have that for you as well after class, after the break. But yeah, somebody asked already, is there going to be more assignments? Yeah, there's the assignment. We have at least chapter 30 and actually chapter 31st. We're kind of going to go over that as well. So I could do a few questions from chapter 30 and more targeted. But I could do both chapter 30 and 31st, but I wouldn't do the whole, like as long as other assignments. Okay, any other questions? Again, I'm not trying to get you worried. You did well in the exam. That's great. I'm just saying that I don't know exactly what kind of a curve situation there's going to be. But yeah, people did well. So let's go through this pretty fast. Again, multiple people got perfect scores here. So let's go pretty fast through the answers, what you were supposed to do. And then let me see, I have the actual numbers for the answers here next to me. I can give you the numbers. Yeah. Okay. So that's the answer. There was C. Both the C again here. So this is something that I did cover. I said that multiple times that solenoids are like for magnetic fields. They're the same thing as capacitors, but for magnetic fields. So for the field is small outside, or if ideally zero, and some value inside. Yeah, no, that's an assumption. The assumption is that the currents are infinite. So remember when we have capacitors, we have the same situation. If the plates were infinite, then the field outside would be zero. But the plates are never infinite. So it's not really actually correct to say that it's 0 outside. It's small, but definitely not 0, because that's only under the assumption of an infinite plate. So likewise here, the assumption is that you have an infinite current sheet. So you have wires that go on for infinite distance. In that case, it would be exactly 0 outside. But of course, that's never true. So it's small, but not really 0. Okay. Okay, for the next one, let's see, which one was it? As usual, a few students got it wrong because of the electron part. So you had to reverse, and so it's to the right. This one, the answer was C, and you have to work the units out, but this one was the only non-zero. So for this one, it was 0, 0. Okay, so let's make sure we understand that. But this one was the only non-zero one, and it wasn't any of the other two. The units don't work out for the other two, right? So it's a torque. So remember what the units have to be: mu and then B, and mu is IA. So A is L squared, is the surface area of the loop. So that's the L squared there. Anyway, most people got this anyway, but more people missed this one and this one, the 6 and 7. This one, it says, what is there, blah, 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 let me see. Oh, is there a flux, right? So this was the case of 0 flux. This is where the loop, the surface area of the loop, and the magnetic field are basically aligned, meaning like they're not perpendicular to each other. So this was the case of 0 flux. I did say I was going to ask this question when I was preparing you guys for this. And here, what's 0 is the force. At the top, on the bottom, the current is aligned with the magnetic field, either aligned or anti-aligned. So that's 0 for both of these guys, 6 and 7. This one, everybody got right, I think, pretty much. We had covered this one, and you remember just fine. So that one was that. I don't think. Sometimes, it's funny, when everybody gets a question, it kind of like the question becomes pointless, right? Because it's only nice because you see that people got it. But it can't, if everybody gets the question, then you can't give grades based on a question. So even though it's very nice that everybody got this one, it didn't help me to be able to say who deserves an A, who deserves a B, and so on. Okay, for this one, actually, for this one, the answers were that one. I actually accepted that as well. I didn't realize it when I gave the question that there was 2 answers that were round off error of one or the other. So I think some people did put, not that many students, but some students did put in that one for the answer. So I gave, just so to let you know that I gave credit. I'm glad I didn't put it directly on Canvas because Canvas wouldn't have done that, but I did it. I gave A or C got credit. For this one, B is the one that is false. We did go over that a bunch of times. But again, most of you did very well on this one, in this part. Now, this one actually caused more trouble. It wasn't supposed to be difficult, but it's easy when you have pressure in your head. It's easy to forget what you're doing. And this is a little bit, so it looks like you should be saying that. So some people did pick that. When resistors are in parallel, the voltages are the same across each resistor. Right? That's the definition of being in parallel. So the answer is actually C. Okay, anyway, I'm spending too much time for things that you guys got anyway. So as I said, most of the scores were pretty high. This one probably is the problem that I gave the most trouble. Even though I said it was going to be there, I covered this in class. When I gave you the practice problem, I gave a practice problem was related, but not exactly the same. Now, I did cover this in class, and I said it could be either one of those questions. This one was asking about the force. So the mistakes that people made here is when they use the B field, mu0 I over 2 pi r, I noticed that some people were using this number or that number or half. So like half the distance or something. This R here is the distance between the wires, because you want to know the B field of one at the location of the other. Now the B fields, it was okay to draw the B fields that way and that way at the location of each one. The main thing, though, that some people did lose points, and I did take it out from the score. If you did, well, the main thing is to tell me in the end, and we did say this a bunch of times, what direction is the force. So what we said is that if the currents in both wires are in the same direction, then the wires attract. So the force, therefore, is like that. So I actually, as long as you tell me the direction of the force, I actually did not take points off if you didn't go through everything, the entire argument. That's fine, as long as you knew that the force is attractive in the end. I gave the full score. But if you didn't say anything about the direction of the force, some people said along the x direction. That doesn't quite clear it up, because along the x direction could be in the positive direction or in the negative direction. So you have to say attractive makes it clear, but saying along the x direction doesn't make it clear. So I looked, in some cases, it was pretty clear that maybe the student knew exactly, but then the words didn't clear it up. And so I couldn't tell, and I looked quite a while. So maybe if that happened to you and you want to show me that, yeah, you made it clear somewhere that I missed, then let me know. But I spent a little bit of time. It was actually pretty easy to grade this exam, because again, people got most of the points. It's a lot easier when people are getting the points. You don't have to start figuring out where they went wrong. So this one was the only one that gave me a little more trouble, but in general, grading this exam was pretty smooth, pretty easy. This one, actually, was kind of an easy question. This one probably was the easiest. So you just had to say what the signs of the charges were. For this part, you were just supposed to derive the formula. So we did that a bunch of times in class. So you're saying that QBV equals mv squared over r. Okay, so that's all you had to write. And then you could solve for r, of course. One of the v's cancels out. Here you just had to draw like this. And so the force is always pointing to the inside, right? Towards the center of this circle that the particles are tracing. Now this one, actually, it was also easy to grade because most of you got the signs correct, but quite a few people lost points, and it's easy to state why they lost points. Almost always they lost points because the formulas they gave me could not solve the circuits. So quite a few students, even though we did say this quite a few times actually in class, we said to solve a circuit, you need as many unknowns as you have equations. But the equations have to be independent. So you say, okay, I gave you 3 loops. Quite a few students did this. Okay, so I did go over this, so I don't feel like at the end this was a question that was unfair in any way, because we spent quite a bit of time on it. And what we said is, if you do 2 loops, then that takes care of all your loop equations. You can't have a third loop. And the easy way to figure that out is to remember that loop equations are only independent if you are including new elements, new circuit elements, and a resistor you haven't used before, a capacitor you haven't used before, whatever. If you write a third loop equation, but you're using the same elements that were already in the other equations, then that's not independent. So 3 loop equations would not ever give you the solution to this circuit. So yeah, people lost a point for that. Quite a few students lost a point for that. You could get perfect credit, but if you gave me 3 loops, that's not going to solve it. You got to do 2 loops and 1 junction. So most of the people that got lost points was for that reason. Okay, but the signs actually were, I didn't find that many people making sign mistakes. So that's fine. And this one again turned out to be an easy problem. Most of you solved it. Some people did not have the right direction for the force. So some people said the force goes upwards. Actually, is the force on this thing opposes the motion. That's the only way it can work out. So the force is this way. Okay, so we did cover that in class. The rest of it we had already, what were the numbers? Sorry. So the numbers were P equals I squared R. So I was 0.7. Well, this is a little bit of a waste of time because you all got it. So, but anyway, so most of the people who lost points is because they didn't get the right direction for the force. But 3 was 37 meters per second. And you get that from BLB. Okay, so that wasn't bad. So yeah, finally, E97. Sorry, is that meant for me, Lee? E97. Am I supposed to know what that means, Lee? Sorry, are you asking a question, Lee? Are you asking a question? Okay, I don't know what that's about. Okay. Okay, any other questions about the exam? No questions about the exam, right? Okay, and again, yeah, I'm happy. I'm not disappointed that I made it easy. It's fine. Made it easy grading for me. I'm sure it was a pleasant exam taking experience for you, except for Long, who had trouble submitting, but that can be corrected. Don't worry about it. But in any case, again, it will make it, it's a little hard for me to know exactly what this means for grades, though, because, basically, I could just ignore the curve. That's one way to go. I'll probably end up doing that. But honestly, let me tell you something that that you should be aware of. That I do notice happens in the final grade that you do get. So this might be my last comment about this, and then I can teach you a little bit of something today, and then we can let it go. Right. So my last comment about this is please keep this in mind, that what happens sometimes is something in the syllabus is not technically worth a lot of weight. So let me get an example for that. Soon, Long. Again, don't worry about it. I have to check your website to see what you're talking about the date of the edit and so on. So I'm grading other exams. You're gonna have to wait a little bit. But don't worry about it. Don't stress out. If it says so on the website on your Google Docs, then I'm gonna look at your Google Doc. So don't mess with it, and it will be fine. So don't worry about it. I'm not gonna forget. I'm not gonna leave a 0 there. That's not gonna happen. Okay. Okay. So. Right. So what I was going to say, though, is one thing that you please do keep this in mind, that when grades are very close together, what can happen, the weight of the exam is the weight of the exam. I already gave you the weights in the syllabus. I forget exactly what I said, but it's on the syllabus, and I'm going to follow that. But what does happen is, even though the weight of, say, for instance, the labs are technically not worth that much, meaning the percentage is only like 10%, whatever. I don't know if it's 10 or 15%, whatever the syllabus says, that's what it is. But even though it's only 10%, what does happen sometimes is most of the grades will be very high, say, but then some student maybe didn't complete the labs, or for whatever reason gets a very low score on the labs compared to the class. So even though the weight wasn't that much, the fact is most students were getting 90%, but you got a 70% on the lab. Well, of course that can happen, and that does hurt a student that is way off the mean. So you got to keep pace with the class, or that can happen. Okay, so so long as you're more or less in the class, then the lab won't make that much difference because it's only 10% of the grade. But if you stray very far from the class, either in the lab or also in the master in physics, that's both weight and the class is doing overall very well. So if the class is doing overall very well, but you're not doing well, then that separates you, and then of course that ends up making a difference. So just please keep that in mind, okay? When you're thinking about your grade. So if you're concerned about mastering physics or something like that, I did say, let me say again that I can open up one assignment again for you for anybody who asks for this at the final week. So in the final week, I'll reopen assignment, whichever assignment you want. You don't even have to give me an excuse. You just tell me, please reopen this assignment, chapter 29. And I will do that I'll give you one more week to complete, but I'm not gonna do that for multiple assignments. So each student gets one assignment like that. If you don't want to ask for any extensions on anything, then that's fine too. But I'll do for each student, I will do one extension on one chapter. Okay. Yeah, that's pretty much everything. I don't have anything else to say. Yeah, people did do well. Good job. And then I will have to figure out what that means. Okay? Right, so I'm pretty much done. I want to just teach you one thing, which I wonder if you've had this stuff about RLC circuits in resonance. Did you do that in the lab yet? I want to tell you what that means. I spend a little bit of time and that will be my goal for today. Once I do that, then I can, and that's it. Have you done the resonant condition in the lab for an RLC circuit? No. Okay, I think you will get to it. So let me tell you what that means. It's kind of interesting how it works. It will, again, I'm gonna get more practical, more specific, more examples on RLC circuits after the break. Okay, so right now we're still kind of still in the theory phase of the whole thing. I don't want to skip the theory phase because otherwise you don't know how people got formulas. So I'm gonna go back to the theory phase of this stuff. Show you more of the theory. I had started to do that already, and then discuss what it means for RLC circuits to be in resonance, which is something you will do in the lab. And the resonance condition is very easy, but I don't want to just give you the resonance condition. I want to show you what the hell is going on with that. To do that, you got to talk about the theory. Okay, anyway, after break, we'll have many examples. We still have time, so there's no reason to. So we'll have examples and specific things of how to. It's a little different. RLC circuits, AC circuits in general, are different to analyze. So you're doing things a little bit differently. So you get still a little bit used to. You gotta get used to what the approach is. So I'll have examples for you to learn how to do that. But I still want to have this PowerPoint that we were talking about to show you these formulas, how they come about, particularly these formulas here, all these formulas. Okay, and in the process of showing you these formulas, I will tell you that using this is pretty easy to figure out what should the resonance condition be and what it means. Okay, so that's my goal for today. How am I doing with time? Let's see, 1 second. Yeah, I have plenty of time. But anyway, I don't want to take the full class, but I'll just explain what that resonance means, resonance condition based on the impedance. So I got to remind you about that. So I'm going to go back up to the top and then stop right at, I'll take 20 more minutes or something like that and stop right at the resonance condition, which you will encounter in the lab. Okay, so, I'm going to go a little bit fast just to get to, so the resonance condition, they're telling you here what it is. There's a graph here where they're trying to tell you, look, when you tune your circuit to have the right frequency, then the reaction of your circuit to the input will be much stronger. So basically you're looking for the current in the circuit to go up. So the resistance of your circuit to go down as much as possible when it's in resonance. So I'm going to show you how that is. Well, in order to figure that out, we have to notice that when we're doing RLC circuits, this impedance. So we had said, okay, when we have an RLC circuit, we have to be a little careful, and we have to define a phase lag. So there is a phase angle there with a minus sign that turns out to play. The minus sign is in this PowerPoint, of course. And then there is this impedance, which is kind of like a generalized resistance of the circuit. But it's a little bit different though, because when you say, if you just have a resistor, the resistor only is not a function of the frequency. If you change the frequency of a circuit, that doesn't mean the resistance is changing in value. Normally, if you just have a resistor like here, R is not R of omega, meaning that's not, R is a value, that's it, you're done. That's the resistance of the resistor. That's not dependent on the frequency that you're choosing for your power supply. But actually, it turns out that when we did the capacitor and we went as far as here, the equivalent thing, so you have a resistance, but for a capacitor, we define this, which people call a capacitance reactance. It's a mouthful. And that is a function of the frequency. That depends on the frequency. There is the frequency right there. Sure, it's dependent on the capacitance, but it's also dependent on the frequency of the circuit, the forcing frequency. So this comes from here, which is the voltage. It comes from the power supply. What is the frequency of your power supply? Just like in the lab. So depending on what frequency you're using on your power supply, then the so-called resistance of the capacitor is changing. So that's different. That's not like the resistor. The resistor doesn't change. It's just the value, whatever the ohms of the resistor. But this is changing depending on your frequency. Okay. And what you have to remember, that came about because you're taking a derivative. Why? So why does this end up having a frequency in there? Well, see, look at what happened. You define the voltage. You use the loop rule. Then you said, okay, now I have the charge in the capacitor. And that's a function of sine omega t. But now I want to know the current. I want to know what is the response of my circuit, the current through the circuit as a result of the applied voltage. Okay. So when I take a derivative, then that's how when I took the derivative, that's how the omega came out here, right? Because, of course, if the frequency is very high, then the derivative is higher. If the frequency is 0, then the derivative is 0, obviously, because there is no change with time, or it takes a long time, so it's taking a long time to change. Well, then the derivative goes down. So, of course, the derivative of the current, dq dt, that's proportional to the frequency. Okay. Then whatever was in front of this cosine of omega t, that's what we called the amplitude of the current. So the thing that's in front. So this thing here, that became the current amplitude. And then what we did is we divided by x. We redefined that, the current amplitude, in terms of the voltage and XC, in order to come up with something that looks like Ohm's law. This is kind of like it's not really Ohm's law, but it looks a little bit like Ohm's law for a capacitor. V equals IR. Well, that's what this is saying. E equals IM XC. But this is a capacitor. IM, sorry. Okay? So this is kind of like Ohm's law for a capacitor. So therefore, what you're saying is, in this funny definition that you're doing just to generalize the resistance, that then the resistance of the capacitor is a function of the frequency. So if you change the frequency, you're changing the resistance of the capacitor. They don't call it resistance of the capacitor, okay? They call it the capacitive reactance, but it has units of ohms. Okay, so we're getting there. And then this is not as important for the resonant condition, but I'll explain this business of our current lagging or leading after the break. Let me just focus right now on this business of just figuring out what does resonance mean, really. Okay, to figure out the resonance condition, we need to figure out what is the capacitor doing. Then also we need to figure out what is the inductor doing. Okay, so now we did the inductor by itself. Okay, and again, please feel free to take the time to figure out that these formulas in the end are not that difficult, but they're doing calculus in there, simple calculus at first, and then when they include several, then it's a differential equation, as you will see. Okay, so now instead of having a capacitor, they put the inductor in there. But you still have the voltage across the inductor, which is L di dt. And then since you can always do the loop thing where you go around and come back, and then you're at the same voltage, then you come up with this equation based on essentially Kirchhoff's rule. Okay, but now you have a di dt, so now instead of taking a derivative, if you want I, that's not what you have initially. Initially you have di dt, not I. Well, then you have to integrate. Instead of taking a derivative, now you have to integrate. So there is a negative sign in there, and then you can rewrite the cosine as a sine minus the angle. So this is, the angle now lags the voltage. We'll discuss that more later, so that bothers students, bothers everyone a little bit. What is this leading, lagging? Don't worry, we have time. This is all we're doing for the rest of the class. So we still have time after the break. Well, we can do review, of course. We can do review as well. But basically, this is the entire new material, is this RLC circuits. Okay, so, but the important thing is when you did that for the inductor by itself, then you can calculate once again something that has the same units as a resistance, so it's ohms, but now is dependent on the inductor. So the inductor, what defines the inductor, the properties of the inductors, is this L there. That's the inductance, right? So since we can now take an integral, integrate that, write it this way, then whatever is in front, that's Im. So that's Im equals to that. This is like your Ohm's law again. Again, it's not really Ohm's law, but I'm just saying it has the same form. Like V equals IR. Now, but R is what in this case? Well, R is XL. And XL, once again, does have dependence on the frequency. Of course. Okay, so it does matter. The response of the inductor depends on the frequency. If the frequency is, of course, if the frequency is very high, then of course there's going to be more effect. Okay, remember that. Why is that? Let me just, this is not so, it's not so mysterious really in the end. Remember what we said the inductor is doing. The inductor is trying to fight change, right? So it's proportional to the rate of di dt, which is the rate of change of the current. So as long as you're changing the current slowly, so the omega is, very small, then the frequency is very large. That causes trouble. The frequency is very small, then that doesn't do anything. So as long as the frequency is very small, you can change the current slowly, and the inductor will act like it's not even there. So it only reacts to when you try to change things, then it opposes you. Okay, so if you're barely changing things, if you're going very slowly, then the inductor doesn't do anything, pretty much. So yeah, of course, that depends on how fast are you making that change, because the IDT depends on that. Okay, so this resistance then goes like omega, the frequency, times L, the inductance. So this has units of ohms. Okay, so that's, people write it like ohms like that. Okay. Okay, so we're ready already for this resonant condition. What is this resonant condition? Okay, well, we're going to skip it. All the steps are in here. So anybody who has the motivation to really dig in and make sure they understand step by step, if you look at this PowerPoint, everything is in there. The signs, everything. Okay, so there's not a single missing thing. Okay, so you could definitely go step by step, but the basic point now is you have to come up with a general solution when you have the three things together. Okay, so now you're going to come up with a differential equation that has three terms. And it's not that hard to figure out what the terms are telling you. This term here, that's the power supply. But notice that, power supply right there. That's how you're driving the circuit. This term here is the capacitor, of course. But the problem here that you have is you have a Q, but the other things are I. So you're going to have to do a little bit more work. You're going to have to do a second order. I'll tell you what you have to do, but you don't have to actually do it. I'm just telling you how this would go. So this is a capacitor here. That's your capacitor term. I know. How did I get this equation? I just went around the loop. And now I have RLC. So I encountered the R, I encountered the L, I encountered the C, and then the power supply, and then I'm back. So that's how I got this. This is Kirchhoff's rule again. That's how I got this equation. So this is the voltage across the power supply. This is the voltage across the capacitor. This is the voltage across the resistor, and that's the voltage across the inductor. Very simple. Some of the voltages add up to 0. Okay? Now, the only complication here, and we're not going to do all the details, of course not. I just want you to see it, that is not, you know, this is not a mystery. You just go systematically doing the right things, and then you get all the answers. To make progress at this point, what you have to realize is that you have a current, I, but this equation that's here, which is very useful, very clear, also has a charge in the same equation. Well, you can't solve it like this. You gotta put everything in terms of Q, or you gotta put everything in terms of I, whatever you prefer. It doesn't really matter. But the connection is that I equals dQ dt. So you need that equation. So what you could do is take derivatives of everything. So you take derivative of everything in this equation, and then you would end up with a dQ dt. You could do it. You could solve it several different ways. Here they're just, you know, they're telling you what this is. So then they're putting it in there. So they're writing everything in terms of I here. So they come up with an equation based on this here. Okay? So they're putting it in terms of that. They're putting everything. They're using what they came up from before, but you don't have to do that. But anyway, they come up with the equation, which basically is the same thing as this equation. And then they solve it for you. You don't have to do it, but they solve it. And what you have to, they do the sine terms, the cosine terms, blah, 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 blah. Okay, great. The bottom line is when they solve the whole, when they have the, and this is series. So this is a series circuit. So it's series with L, not parallel. There's nothing parallel here. So therefore, there's only one current, right? So it's the current through all three things at any one time. You can't pick I1, I2, I3. No, that's wrong. That would then you couldn't solve it. You have just one current, is the current of the entire series circuit. Okay, so if you do that, then if you're gonna define this as the amplitude of the current, IM is the amplitude of the current, then this is the voltage, and this thing is the impedance. And notice what the impedance says. If you want to calculate the impedance of all three elements, we already have decided R is for the resistor, XC is for the capacitor, XL is for the inductor, but now you have them all together. So then, in that case, is R squared. These still have units of ohms, still ohms, same units, by the more general formula that includes all three elements, right? The resistor, the inductor, and the capacitor in one formula. Now, I'm already have enough here. I'm gonna just say one more thing, and I already have enough here to tell you what it means to be in resonance. Okay, what it means to, you could think of it either one of two ways, it doesn't matter which. What you can have, a circuit in resonance is one in which basically what you're trying to do is find the frequency for which the capacitor and the inductor cancel each other. Okay, in that case, it's almost at that frequency only, is as though you only had the resistor. Okay, so how are you gonna get them to cancel each other? Well, if the capacitor and the inductor cancel, you can think of it either way. You can say, okay, if the capacitor and the inductor cancel each other, then there should be no phase shift. So one way to think of it is to say, oh, when is this true? That's one way to think of it. When is the, sorry, I changed the symbol. They have this symbol. I mean, it's close, but not the same symbol. Okay, so that's the phase angle. So for what value is that 0? Another way to think of it is, same thing, is for what value, for what frequency is C gonna be the minimum it can be? Okay, So how can you get the impedance to be the least possible amount? So how are you gonna, let's do that one. It's the same condition, but let's do that one. So if you wanna make this as small as possible so that there's less resistance to the current, then how are you gonna do that? Well, you're gonna try to get this to cancel that. So you're gonna say XL minus XC equals 0. But they're telling you what XL and XC are. So let's see if that you could do that. See if that's possible to do. You normally that wouldn't be possible because you would think that the resistances are independent of frequency, but they are dependent on frequency. So let's see if we can make that 0. If we can make that 0, then the impedance for this value, where this is 0, will just be equal to R. Right? Everywhere else, you add another piece, but any other frequency, you would add another piece, so the impedance would go up from this value. So basically, as though the impedance at this frequency, the impedance is exactly the same thing as the resistance of the resistor. Okay, so the C equals R. Okay, so if that's true, then we have to find for what frequency is this possible. Well, it's not very hard. Let's do it. So you say omega L, right? That's this one, minus 1 over omega C equals 0. At first sight, it's going to seem like you couldn't do that, but actually you can, because the capacitor and the inductor kind of work in opposite ways. So it turns out you can cancel them against each other for one particular frequency. So then how will you do that? Well, you just would multiply both sides by omega. So you would get omega squared L equals 1 over C. Oops, it did that automatically. 1 over C. Okay, or you could write omega squared equals 1 over LC. So then you could take the square root. So you could say omega, sorry, I'm writing all over the place, equals 1 over the square root of LC. So only for this condition, only here, what will happen is that the capacitor is kind of undoing the effects of the inductor. And it's as though for that frequency, the only thing you have left is the resistor. Okay, so that's what you're doing by tuning. That's what you're trying to do. And actually, this is one of those labs that is sad not to do it in person because it works perfect. It's not like one of those things. You can find this frequency very easily in the, you could do it several ways. You can see you can try to keep track of the phase angle. And then you can see that there is a phase angle. So in your oscilloscope, your wave patterns, your sine is a little bit out of phase. Your voltage, you can put your voltage in the oscilloscope, and then you can put your current in the oscilloscope. And they're always out of phase unless you tune the frequency to this particular value. At that point, they're exactly in phase because the resistor doesn't change the phase angle. Okay, so now you found the resonant condition. You found the condition, the frequency for which the capacitor and the inductor cancel each other out. Okay, so that's a good place to leave it. Yeah, I like to keep this in there. Do not be afraid that in the exam I'm going to get practical. I'm just going to do examples and so on. But it is nice to have the right way. You know, this has all the details. Your PowerPoints don't have all the details. So if there is any doubt about what the definition of anything is, if you go back to this PowerPoint, you can clear everything up exactly. What is it that you're saying? Okay, the bottom line in the end, please don't get too afraid, because in the end, really in practice, you're just gonna probably start all your problems, the problems you could encounter in the exam, everything else, you're gonna start from this set of equations. Okay, so you won't have to remember all the other steps above. Just starting from this as the starting point will be fine, but it's nice to know how we got there. Okay, it's not, instead of a big mystery how you put that, what these equations mean. Okay, anyway, so let's stop there though. I don't have anything else to say about the exam. If somebody has some pressing issue that they want to discuss about the exam, something, then let me know. But that's it for today. Have a good break. Thanks for letting me know about no class on Wednesday. That definitely helps. So I'll send an email in case somebody doesn't know that, like I didn't know it. I didn't remember that part. So I'll send have a nice break, everybody. So if somebody has a present issue, please hang around. I'm gonna go get some coffee and come back. If anybody's still around, we can discuss whatever your issue happens to be. Okay, if you sent it to my email, it wasn't just Long. I think there was somebody else sent me something to my email. I'm not really sure. If you did, I didn't get to yours yet, to your exam. Have a good break. All right, quite a few of you. Wow. Let's see. Long, we already talked about your thing. That's not, I don't have your exam, so I couldn't discuss grades with you. Okay. Do you have something else to discuss?
No, just about my test because it's kind of stressing me out. No.
No, I know, but I'm telling you, I know you're getting stressed out, but I'm telling you, if I go to your website and it says the right time, and then I know what time the exam was.
Yeah.
So as long as it says last edited by such and such a time, then I will just take that. So Now I have to see that, but you're telling me it's there, so I have no reason to doubt that.
Okay. Yeah, that's about it.
If you want to send me to me one more time that link, send me. Why don't you, instead of all the other emails, send me one more email? Just send me that link where you say the your Google Doc that says last edited.
Okay.
And
So
I'll just go right to that email. I'll check that when it was last edited. If it was within the time frame of the exam, I'll just download that document, and then that's it.
I did send you an email last night. That was when I.
Okay.
But I'll send you another one right
Well,
now,
that's fine. Then don't
just
do it.
with the link
I'm saying I
to the
didn't
document.
do it. Okay. But right now, I'm not sure why you're hanging out, because there's nothing else. You're not going to end up with a 0 long. So that's all I can tell you. At this point, obviously, I haven't graded your exam. Okay. No. You're still hanging out. I'm not long. There's nothing else to say. I'll check the email. That's it. Okay. Will you be grading the exam that was sent to you by email? Yes, I will be grading the exams. And again, if it wasn't submitted very late after the due date of the exam, then I won't take points off. It's a little bit of a matter of judgment. If it's 15 minutes late, then yeah, I would take that's 15 minutes you got, somebody else didn't get. But if it's just like a couple of minutes, then no, then I won't take any points off. Okay. Anybody else? Any other questions? That it? Okay, well, I'm not getting any other